8 o'clock, we should probably start. So hello everyone. Welcome to the One World Combinatorics on Words seminar. Our speaker today is Mélodie Lapointe from the University of Moncton, and she's going to speak to us about perfectly clustering words, induction, and morphisms.
Okay, hi everyone. Thank you for the opportunity to speak. So what I will present you today is a perfectly clustering world, but mainly I will focus on morphism that allow us to send perfectly clustering world to another perfectly clustering one. So basically, those family of morphism allow us to enumerate them directly without checking every world on every possible world. And from the morphism, you can naturally deduce an induction on discrete interval exchange transformation. So I will talk a little bit about how you construct that induction and what are the link between the morphism and the inductions. And finally, so the first two things were our work that I've done during my PhD thesis. And after that, by kind of coincidence, we observed that there is a relationship between a perfectly clustering world and the band breaks representation of certain algebras. So I will talk a little bit about what are the band breaks algebra, and what are the relationship between these two results. So what are perfectly clustering worlds? So they are defined from the Burrows-Wheeler transform of a world. So the Burrows-Wheeler transform is a function on worlds that is defined as the following. You first of all take all the conjugates of the word that you want to compute this Burrows-Wheeler transform. For example, if I take the word ananas, all its conjugate, I simply rotate all the letters one after the other, so I get 6 different words. After that, I need to sort them in lexicographical order. So the lexicographic order is simply the order of the dictionary. So I use the natural order on the letter. A is smaller than N, which is smaller than S. And we sort them as in the dictionary. So we took the smaller factor and go on like that. So you get a tableau like this. And the Burrows-Wheeler transform will be the word which is the last column of the tableau you obtain from the top to the bottom. So in the case of ananas, the Burrows-Wheeler transform will be S N N A A A. And a perfectly clustering world will be, okay, so in this talk, I will represent W between bar with a small a to denote the number of occurrences of a letter A in W. And a world will be pi clustering if its Burrows-Wheeler transform is sorting the letter. So each occurrence of a letter will be in a block, and the order will be determined by some permutation pi. So just note that pi cannot be the identity. And this is just because of the way you define the lexicographic order. If the word is ending by the smallest letter, it means that it's not the smallest conjugate. So it's impossible to have the identity permutation. And a word will be perfectly clustering if it's Burrows-Wheeler, the permutation giving its ordering its letter in the Burrows-Wheeler transform will be the symmetric permutation, meaning that the biggest letter will be in first, after that the second biggest, and etc. And you will end with the smallest letter. So, for example, if we take the word appartement, okay, so the example is I mixed my slide, and the word in the example are in French, but so the first word is appartement. And if you compute its Burrows-Waller transform, you get the world at the bottom. You see that this world is neither perfectly clustering or pi clustering, because the P here is between two of the occurrence of T, so the letters are not sorted in any order. If you take the word aluminium, you see that it's pi clustering, because each occurrence of each letter is grouped together. So you get the occurrence of M, N, A, U, I, and L. But it's not pi clustering, because, for example, the A is the smallest letter, but it's appearing in the middle. So it's pi clustering for a certain permutation. And the word anana will be perfectly clustering, because it grouped together all the occurrence of the same letter, and the biggest letter is the beginning, and it's go on like that. So basically, the result of the Burrows-Waller transform will be a decreasing world. I just want to mention that if you look at in the literature, you can also find those words under the name words with simple Burrows-Waller transform. So why do we want to study perfectly clustering words? But first of all, if you look at them on the binary alphabet, they are exactly Christoffel words. It was shown by Mantasci, Restivo, and Scortino in 2003 that if a binary word is perfectly clustering, if and only if W is conjugate to a Christoffel word. And the other interesting result is that they are acting as interval exchange transformation. It was shown by Ferenczi and Zamboni in 2013 that if W is perfectly clustering, that the mapping from the last column to the first column is a minimal symmetric discrete interval exchange transformation. So I just want to recall, we won't use it much, but I just want to recall what is a Christoffel word, so anyone can know why they are important. So Christoffel words are the words that encode or represent the line with rational slope. So for example, here we have the line with slope 7/4, and you see that the word AAB, 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 AB is the better approximation of that line in the discrete plane, and this is the Christoffel word associated with that line. They are also known as standard words, central words, or periodic mechanical words in the literature. And they have been studied a lot. We know a lot of combinatorial property of those words. Obviously, if these words have a lot of property, there are not only one way to get a generalization, because when we add letters to the alphabet, we add liberty, and not all the property will be preserved. So perfectly clustering words are not the only possible generalization of Christoffel word. Another generalization which was already present and studied in the literature is finite epistolian words, which are factor of infinite epistolian words, and an infinite epistolian word is a word W on an infinite word W, such that it should be W here. So every factor of W, so the set of factor of W is closed under the reversal, which means if W is a factor, then W is a mirror image. So the word read in the reversal order is also in fact of W. And at most one of its factor is less special for each length. So yes, and it's interesting to study perfectly clustering words, because even though on the binary alphabet they are the same family of words, on the ternary alphabet and beyond they are not. So epistolian and perfectly clustering words are not the same set, but they still have common intersections, which in fact coincide. So a word is both episturmian and perfectly clustering if its factors are circularly balanced. This is a good thing because on the binary alphabet, every Sturmian word or every Christoffel word is circularly balanced. This is why the intersection is the whole set on the binary alphabet. This was studied by Restivo and Rosen in 2009. Okay, so this is what was in the literature before I start my research on them. So the first thing that we wanted is that for Christoffel words, we know that if we use some morphism, namely the morphism G, which send A to A and B to AB, and D type, which send A to AB and B to B, you can construct a sequence of morphism starting from AB, such that you will obtain the word W. So this was already known by Berstel and De Luca. There's a lot. Most of the time, you won't see the results state like this, but there is a lot of way to construct that sequence of morphism, and they are really well known. I just want to recall that a morphism is a map between the monoid A star to A star, such that for any word U and V in A star, it should be A star here, phi of UV, so the concatenation, if I apply phi on the concatenation of UV, it's the same as applying the concatenation. It's the same as taking the concatenation of phi of U and phi of W, like that. So can we describe a perfectly clustering word in the same way using only morphism? Simpson and Puglisi have already tried in 2008, and what they so they obtained something on the ternary alphabet, so on the alphabet ABC, but their sequence here wasn't morphism. They only got function. So they got three objects, psi, theta, and phi. And the first two are, if you check their definition, they are morphism. But the third one, it's only a function, and you cannot transform it into a morphism. And it's really complicated and really dependent on the alphabet, which means that it's really hard to extend on the alphabet with 4 letters or 5 letters and get interesting results with that. This is why they basically did it for the Ternary alphabet and probably stopped there. So our solution to that problem was to take free group morphism instead of monoid morphism. Just to recall some definition about the free group generated by the monoid A star. If it's that we will take the inverse of an element will be denoted by L exponent -1, and each element of the free group can be represented by a reduced word, where in fact we don't the word won't contain the factor x or x -1 or x -1 x. So the only reduction that we apply on word is that we don't allow to have a letter and its inverses following each other. And an element of the free group is called positive. It's if it's an element of the free on the not the free group but on the monoid. So what we obtain is for the ternary case, what we obtain is a family of 3 morphisms and their inverses. We will need to use to also use the inverses and two morphism on the free not on the free group. They are on the free group, but they only contain positive letters, so you can view them on the monoid directly. So these two, what they do is that they take the two-letter alphabet AB, and they send either to itself, AB, or to the alphabet BC. Because the way that we do our construction is we take a Christoffel word, so a two-letter alphabet word that is perfectly clustering. And from that, we can obtain every perfectly clustering word. So this allows, but for the construction to work, we also need to use the Christoffel word on the alphabet BC. So this is why we use the F, B, and FE. So we only use them at the beginning just to place the Christoffel word on the right alphabet. And after, we use a sequence of morphism taking from lambda ABC or the inverses. And we get, like that, we can get every perfectly clustering word. Evidently, the sequence here, G1 to GK, has some, there are some restriction on how we can use them to get a positive word. Just note that the lambda A, lambda B, and lambda C are easy to generalize because if you take the natural order on the alphabet, so A is smaller than B, smaller than C, lambda A will send A to itself, and after that, it will just add A to the other letter at the beginning. Lambda B will send B to itself, will send C, which is bigger, to B concatenated with C, and it will send the smaller letter A to A concatenated with the inverses. And lambda C is defined similarly. So what we get is that in the general case, so if we have an alphabet AR with a natural order A1 smaller than A2 smaller than AR, you can define lambda help of the letter A by saying if I have a letter smaller than A, I just put A in front of the inverses of n minus 1. I send A to itself when A is my special letter. And after that, all the letters bigger are sent to themselves concatenate with A. Not themselves. My special letter concatenate with A. Rho here is only the definition of the inverses of lambda, and it's basically the same thing. So, but the smaller letter are sent to L instead of n minus 1, and the bigger letter are sent to n minus 1 instead of L. And we also need the function f, which will send a word on the alphabet AR to the alphabet AR plus 1. But basically what it will do, it will choose a letter and it will cut the alphabet there. So you will send the beginning of the alphabet to itself. And after that, you will just skip a letter and all the other letter will be sent to the next letter in the natural order on R plus 1. Like that, and you will get the theorem that says that there exists a sequences of group morphism like that, G1 to GK, such that if I apply my sequence of morphism on A, I will get my perfectly clustering word W, and the GI in the sequences will be given by lambda, the lambdas, the rows, and F concatenate with lambdas and rho concatenate with F, which will allow, which means that I will always have words on the alphabet AR with every letter appearing in it. So I don't want to apply F alone because otherwise I will have a word on the alphabet AR with the missing letter, and I don't want the missing letter. So this is why I use F concatenated avec rho. And if you look at the beginning of the theorem, I said that I obtain all the Lyndon complete perfectly clustering word. The complete here only mean that every letter in the alphabet appear in my resulting word, W. And Lyndon here is just because the Burroughs-Polar transform of a word will be the same for all conjugate of a word. So I will always take the smallest one, which is the Lyndon one, in my conjugacy class. which and to basically to enumerate all perfectly clustering world, I will restrict myself to enumerate all classes by choosing one representative in each classes. In that case, it will be the Lyndon world. So if you look here at the world in purple, this is a perfectly clustering world. You can check by computing its Perot-Square transform. And its sequence of morphism will be this one. There might have other one that can fit, but I won't talk about it much here. But basically, in my thesis, I construct a tree which allow me to enumerate all of them and get the sequences to all of them. Yeah. So the proof of that, there's many steps to get the proof of that. I just want to briefly talk about what are the main steps and the main difficulties. First of all, even though lambda L and its inverse are inverse morphism, I also need another relationship between both of them to complete the proof. And it's that if I compose them with tau, the reversal of the mirror image of tau, this is an antimorphism, I will get the other one on the reverse alphabet. So just to be clear, tau is the morphism that take the alphabet and send the smallest letter to the biggest one, and so on until it reaches the biggest letter, which will be sent to the smallest one. So for example, on the alphabet ABC, tau will send A to C, B to itself, and C to A. I take the mirror image, so I take a word and I reverse the order of the letters. And one important property is that if a word is perfectly clustering in, then its image under the mirror image tau is also perfectly clustering, which is false if we take only one of the two morphisms. So if we take the mirror image, you won't get a perfectly clustering. No, okay, if you take the mirror image alone, you will get a perfectly clustering world, but it will be in the same conjugacy class, which is not interesting in that case. And if you take only tau, you won't get no, you will get also a perfectly clustering one, but it won't be the smallest one. So by taking both together, you get the smallest you get the smallest one, which is what we want. And basically, most of the work is to show that if I take lambda L of W, where W is a perfectly clustering world, then the image will be positive and perfectly clustering. But there is a condition, which is a condition on the letter that appear in W. So if I have so if I take a letter A, it has some position in my pairing vector, if you want. And if the sum of the letter bigger than my special letter L is bigger than the sum of the smaller letter than L, then I know that this word will be positive and perfectly clustering. And basically, if I have the other condition, so if my letter bigger than L or smaller, the sum of them is smaller than the letter bigger than L, I will get that the inverses will be positive and perfectly clustering. So this gives me the condition of when I can apply which one. And for the positivity it's basically just studying the factor in the perfectly clustering world that can appear and check cases. For the perfectly clustering part, it's really used. I really use the relationship between Perot-Square transform and discrete interval exchange transformation. I basically prove a relation between both of them to get the result. And yeah, so this is you can obtain that. And for the proof that I both morphisms and Lyndon wall to Lyndon wall, so the smallest one. This is kind of strange, but you can show that if you take the map lambda L inverse as a map from A star to the monoid, A star union its inverse letter, it will be increasing if you take, and the order that you need to take on A star, on A union A inverse star, is that you take a letter, it's smaller than its inverses, which is, and after you continue with the next letter. So you just insert all the inverses between any pair of letter, of positive letter, and you will get that this map is increasing in that setting. This is, you need to be very careful because this is false if you take lambda. So you really need to take the inverse of lambda and show it on that. And after you can take any Lyndon word on A star and show that if its image is positive, then it will be a Lyndon word. So we don't even need the fact that it's perfectly clustered. And to show that lambda L, if lambda L of the value is positive, then lambda L of the value is a Lyndon word. We will take a perfectly Lyndon word, and we will use the relationship at the top here to show that you get also a Lyndon word. But you won't have the first map. The first property is false if you try to show that this map is increasing. And if you take in general any Lyndon word, even if its image is positive, it won't be necessarily a Lyndon word either. So you really, really need the fact that they are perfectly clustering in that case. So one way to see why this happened is that there is no symmetry between the lexicographical order. So it's really dependent on the order on the alphabet. And so this is kind of a special property that on perfectly clustering word, there is a symmetry that helps to preserve the smallest word in the conjugacy class. So as I mentioned earlier, one on the to show that the morphism preserve perfectly clustering word, we need the relationship between perfectly clustering word and discrete interval exchange transformation. So this naturally leads to an induction on them, which I will briefly describe here. So just as a reminder, a symmetric discrete interval exchange transformation, you get a vector of length. So here we have R interval and the C1 under cardinality of each interval, defined on a set of the number of points contained in the interval. So for example, here I have 3 intervals. The first one has length 5, the second one 4, and the last one has length 7. And the symmetric case means that I send the last interval at the beginning, the middle interval at the middle, and the first interval at the end. And what I want to study in that setting is the trajectory of a point. So I put a point here. I put it in the first box, but it can be anywhere. And I look at is displacement induced by the function. So if when I am in the first interval, I will use the letter A to encode the position, in the second the letter B, and in the last one the letter C. So when I apply my transformation, once I am in the red interval, so I write C, and if you continue, you get on the blue interval C, and if you go on, you will obtain a word like that. So since we are in the discrete case, we know that the world that will be obtained will be ultimately periodic because there is only a finite number of boxes. So at some point, I cannot reach new boxes. So the world will repeat. What we are interesting is that is when such trajectory is contained goes to every box. So for example, in that case, if you check the number of letters, this is one period, and the number of letters is coincide with the number of boxes. So you get that the trajectory is minimal, which is the case which will interest us. So what it means for perfectly clustering world is that if you take the tableau that I've constructed in the beginning, where I have all the conjugates in lexicographical order, if you take the first and the last column, you get essentially the interval and the transformation. So this will be the interval on the top, and this will be the interval at the bottom. And the trajectory will be, in fact, if you start at the first box, the trajectory will be the world at the top here. And it will be minimal since I know that, yeah, and you can show that it will be minimal. In fact, Ferenczi and Zamoni show that in that case, it will be minimal, always. So what happens is when I do the morphism, I change. So here, basically, the number of letters give you the length vector of the discrete symmetric interval exchange transformation. So when I apply my morphism, I modify that length vector, which is similar as an induction. And if you want to describe it as an induction of the minimal symmetric discrete interval exchange transformation, you take the partition of the interval at the top, which I call A, and the one at the bottom, which would be simply the, you apply the transformation on the interval at the top and you get new intervals. And we define the intersection between the interval at the top and the bottom. Since the permutation is symmetric, the middle point of the transformation will be in one of the intervals. Not necessarily in one, it can be between two intervals. In the case, we won't check it there, but in the case if it's between two intervals, basically what I have is you remove completely an interval and you get on a smaller, you get R-1 interval instead of R. But in the case of n of one of the NA is non-empty, you denote this letter by B and you get a new discrete interval exchange transformation on with K interval defined by you take the IA previously by minus, you take all the interval you have at the beginning except the one that is the one with your special lantern that the intersection is non-empty, and you replace this one by its intersection, and you will get a new discrete interval exchange transformation with at most K interval. So here I have an example. So you got the lambda B morphism, which sends this perfectly clustering one to this one. I write the B minus B inverse B in red because they don't appear in the finished solution because they are not reduced. So the world we obtain at the end is ACBBCACB, and if you take the discrete the interval exchange transformation of this world, and you take you see here that the non-empty intersection is for IB, and you replace IB, you get a new transformation which will also be minimal. And this is a really important fact to prove that the morphism preserves perfectly clustering world. Okay, so to finish my presentation today, I just want to present a new application of perfectly clustering world. But what is really interesting, it's also a new application of Christoffel worlds. So it was not known even on Christoffel world previously. Okay, so all of the band-breaks module are defined on a general algebra lambda n, big lambda n, which is defined on the quiver Qn. So you just have a directed graph with vertices 1 to n, and each vertices is linked to its previous vertex by 2 arrows in the same direction, like that. So, okay, so technically it's a multigraph. It's a multigraph, not a graph. And you have some relationship that are impossible. So if you walk in the graph, you cannot take B2 and alpha 1. So some paths are not possible to follow. And this quiver and relation give you basically the generator and the relation of the general algebra. The way to study its undecomposable representation. Okay, so its undecomposable representation are known. They can be described by string representation, which are just a word, which is a path in the graph, and its band representation, which are non-oriented cycles. This is where we will use perfectly clustering world. We will see them as a cycle just by taking the conjugacy class. Okay, so to define a cycle in Qn, the cycle I have very precise form. So you start at 1, you go up to a certain vertex I by taking the arrow alpha, and when you are there, you come back to 1 by taking the inverse of beta, the arrow inverse of beta. So this is all the cycle that we will study. And if we have a word on the alphabet A1, on the monad A1 to N, we define the cycle of W by taking the ZE cycle for each of the letters. And the main result is that if I have a primitive word on n letter that is perfectly clustering, if and only if the band module defined like this, where I got my cycle phi of W, is a break for some lambda in the algebra, in the field K. So just to be clear, a representation M of lambda n is called a break if its endomorphism space is isomorphic to the algebraic field K. And okay, so this is the main theorem, but what I want to explain is how we obtain that result and what are the links between the two. So first of all, we use perfectly clustering world and the Burrows-Waller transform, but in fact, to get the proof, it's easier to work with the Gessel-Reutenauer bijection, which is a generalization, And if you take the Gessel-Reutenauer bijection, the Burrows-Waller transform will be a particular case of that transformation. So of the inverse of that transformation, it's important to know which way you go. So the Gessel-Reutenauer bijection is a map that sends a word W in A star to a multiset of primitive necklace. A necklace is simply a conjugacy class of a word. So this is why I wrote the word in parentheses to mean that I don't mean exactly the word B-A-A-B-A-C, but the word, all the conjugate of that word. So you first compute the standard permutation of W, which is simply you you take your word W and you take the first letter, and each from left to right, you give a number to each occurrence. So the first letter of A will be 1, after that 2 and 3, and after you take the next letter, so B will be 4, 5, 6, and after the next letter, donc C will be 7 and 8. You get a permutation like that. You compute the inverses, so you just compute the inverse permutation, and you take the cycle of the inverse permutation, so you just read the cycle. And by replacing the EM letters, so if I take a circle, for example, a cycle, if E is 1, I will replace 1 by the first letter in W. So 1 will be replaced by B, this 2 will be replaced by A, the 3 will be replaced by A, the 7, 1, 2, 3, 4, 5, 6, 7 is also A, and the last letter, the last number is 4, which is C. And you go on, and you get a multiset of circular world. We take a multiset because some world might be, some conjugacy class might appear more than once. This is already known that the perospheral transform is a particular case of the inverse of the bijection for some time now. But okay, and what happened is that on the algebra, they studied the break representation by taking surfaces, polygonal surfaces like that, and drawing path on them. And when they do that, they can represent this by a Dyck path, which represent the orientation of the arrow and the number of intersection with the curve. So for example, here 5 is 1, 2, 3, and you get the last component is 3. So the 5 is appear 3 times. So like that, they construct a Dyck world, and they can recover the curve on the Dyck world just by drawing a line between one side of the Dyck world to the other one without crossing. So here the 1 goes to 3 and the 4 go to 5 because we don't want to go outside of the Dyck path. And by walking on that curve, they get a world, which here we can read like that. So the walk is kind of a little bit weird. You go from 1, when you arrive at 5, you need to go at the other end of the number of occurrence of 5 because when they glue the polygon together, they reverse the order of the arrow. So this is why we jump to the 5 at the top, and you continue your walk on the path. So 4 need to be identified with its inverse friend. So you jump to the other 4 and you walk, and you go like that, and you will get some necklace on the alphabet, 1, 2, 3, 4, 5 in that case. And so, and the really nice thing about that is that the Dyck world here is represented by simply a vector, which is the number of occurrence of each letter, while the minus represents the up step and the plus the minus step, the down step. And basically, if you have a perfectly clustering world, the Dyck world, the Dyck path will be just you go up, and then you go up and you go down after, and the number of times you go up is simply the sum of all of the time you go down. So the left side of the drawing will be just the same letter repeated n time, the number of time you go up, and the other side will be a certain number of down, which be exactly the same number of down, but will be split in n-1 interval, representing each of the letters. And so you can define them. So yeah, basically, if you do the walk to get the on the path to get all the letters, and you remove the first letter, since it's the one you go up always, you don't want to consider this one, so you just use like the erasing morphism that set 1 to epsilon, and any other letter for the other. And what you will get is a phi of the word on the alphabet n to 2. It's just a technical choice that we choose to use the alphabet n to the alphabet 2 to n, but it's the same as if you take a to a-1, it will be fine. And so here, if you take the Gessel-Reutenauer bijection of the weakly decreasing word, the word that you will obtain is a perfectly clustering word. Yeah, so using that, you get the previous theorem, which means that if a word is perfectly clustering, if and only if it represents a big brick module, a brick bound module. And one interesting fact that you need to show to obtain the result is that if W is a weakly decreasing word, so just meaning that it's a word n, the word n, a1, a, n time, and you go down like that, then each circular word in phi of in the Gessel-Reutenauer bijection of W is perfectly clustering. And this is kind of easy to see if you think about it. You just take a word, a necklace U in phi of W, and you take two of its conjugates, which are not equal. And we know that if two words are consecutive in the two words are in the okay, so the order in the tableau of phi of W is simply U1 at repeated infinitely many times is smaller than U2 repeated infinitely many times. But since our words have the same length, since they are both conjugate of U, it only means that U1 is smaller than U2 in the lexicographical order. So if the phi of W is weakly decreasing, it means that we have that the last column in the tableau of U is also weakly decreasing, which means that U is also perfectly clustering. Like that. And one interesting result that we got from there is that if you take the Gessel-Reutenauer map of the weakly decreasing world, and you can obtain a perfectly clustering world, or you can obtain a multiset of words. And in my thesis, I conjecture that the number of length of such words must be at most n-1 C divided by 2. But using linear algebra and the construction that we made in the paper, we were able to show that the number of distinct conjugacy classes of a word appearing in the Gessel-Reutenauer bijection of weakly decreasing word is at most n-1 C divided by 2. So not only the number of possible length, but also the number of distant conjugacy class is bound by that. So thank you. And if you have any question, just ask.
Thank you, Mélodie. Does anyone have any questions? Christophe?
Yes, hello. Merci, Mélodie. Thank you for this talk, this nice talk. And I had a question I had two questions. when you say that you define these intervals n indice A, comment dire en anglais, NA, and
Yes.
You say there is one which is non-empty. At least
Okay.
one. I didn't understand this well.
Okay, so there is not always one. If there is one, okay, so the idea is that we want to induce on the middle point, the interval which contains the middle point. So since I have a length, I can find the middle point just by summing all of them and divided by 2. And this point can be in an interval or between 2 if it's 1/2. Because we divide by 2, it can be odd. So it can be in neither. But if it's in an interval, the intersection between the top and the bottom will be non-empty, and you can induce on that. It's just a reformulation that's what I've done in my thesis, but.
Yes. Okay. I have to look closer, I think. And
Yeah.
yes, my other comment or question was about these morphisms. Did you look if, I think it would be interesting to look to the action of these morphisms on palindromes, perhaps palindromes in the free group, appropriately generalized. Of course, they will not preserve palindromicity, but almost like these, the morphism of G and D tilde, or these morphisms, the standard, the normal, the regular, I mean, the classical Sturmian morphisms almost preserve palindromicity almost. You must just add a letter at the beginning or at the end. And I think perhaps it would be interesting to look it in for viewer morphism, if there is something similar.
I did not, but yes, it's a good idea.
Finished, yes.
Okay, thank you. Hajime, did you have a question?
Oh, okay, thank you. Thank you for your nice talk. So I have a question about the motivation of pi clustering. So you did define the general pi clustering. So what were the motivation for defining the pi clustering?
Okay, so I defined pi clustering just because the result of Ferenczi and Zamboni is true for pi clustering. We don't, after that, all my results are only valid if you are perfectly clustering, but the Ferenczi and Zamboni result is true for any pi clustering world.
So your result is applicable for, so is it possible to generalize your result for general pi clustering?
Maybe, but there's some symmetry that are present in the symmetric case, which are not present if you take pi clustering, and I'm not sure at that point how to deal with that.
Okay, thank you.
Thank you. Are there any other questions? If not, thank you again, Mélodie.